Hello, and welcome to the eighth in the series of customer webinars. My name is Rajiv Kumar, and I'm the Director of Marketing for Virginia Transformer. And along with me is Parminder Panesar, who is the Technical Director, and Balakrishna Mani, who is the Supervisor for the Research and Development Group. Hello, and welcome to the eighth in the series of customer webinars. The topic for this webinar is transformers for special applications. This webinar is being recorded and it will be available on our website, and this will also go on YouTube as well, where it will be available for future viewing. If you have any issues in getting a link to the webinar recording, you can always reach out to the marketing email ID in the invite, and we will link you up accordingly. I would like to now invite our technical director, Parminder, to give an overview of what are some of the transformers we see commonly for special applications.
Thank you, Rajiv. There are many applications for transformers in the industry, but in this webinar, we can concentrate mainly on three major classifications here. First is rectifier transformers. So these transformers, I'm going to brief about each one of them here. They are multiple low voltage winding, so that they are phase shifted wave shapes, which gives lesser ripple effect when they pass rectifier. One of the most common applications for this is the transit duty. All these transit railroads for various metros, they have these kind of transformers, and they are generally 12 pulse or 18 pulse, mostly 12 pulse, because they're more simple than other one. And in these, actually, IEEE defines the various types of duties for these transformer, and heavy traction, extra heavy traction, and we will go through those details in the webinar. The second application, which is very common in the utility market, is voltage regulators. So these are, as name says, they regulate the voltage. They don't have stepping up or stepping down capabilities, but that one actually is only regulating within plus minus 10% of the input voltage. A lot of utilities who do not have transformer with lower tap changers, this is the common practice they use to give consumer the right voltage as they need. And third one is more for the system configuration and the protection point of view, is earthing or grounding transformers. So these transformers where the system does not have grounding point, if it does not connected, and customer needs the transformer to have a ground point to limit the fault current, that's how where they are used. So all of these transformers, the application which we discussed in the previous slide, it is possible to make each one of them in either liquid or dry types, depending on the rating of the transformer size, kVA, or the voltage class, users site limitations. So they will decide which type of transformer they want. Liquid are most common, and there's pretty much no limit to the size of transformer and the voltage class of this one. So and under liquid, there are regular mineral oil or inflammable, which are natural esters, so less flammable and liquid, so we could use those. And so depending on where the location of these transformers are, and based on that, customer will have their own site code to follow, and they may go for less inflammable liquid, and then otherwise mineral oil is most commonly used. And when we go to dry types, there are two types of construction which VTC makes. One is VPI, which is using varnish and vacuum pressure impregnation, and that one is one objective. Second one is totally encapsulated coils, which is VTC's brand name Uniclad. So in this, the all coils are completely encapsulated and protects from dust and other humid environment conditions. So those are another two possibilities. Third one is gas coil, which we are not in the business, but it is similar to Uniclad, but has a higher chance of partial discharges. So that's the reason our business limits us to Uniclad. So those are the few construction-wise we could do. Let me invite Bala now to talk about the standards which these transformers are built to and how it bridges the specification between consumer and the manufacturer.
Okay, thank you, Parminder. The standards, we have a few different standards which covers the special transformer requirement, and starting with IEEE standard C571810. This standard is for semiconductor power rectifier transformers, which include both single phase and three phase, and for both liquid and dry type. This standard is very detailed. It covers all the service conditions, usual and unusual, then rating data requirement. Then we have impedance and commutating impedance requirement and the circuit types. And very important thing in this standard is it covers the harmonics requirement and the loss calculations for the transformer to withstand those harmonics. And also it has the details of testing requirement. So for these transformers, you need to feed in additional losses based on the harmonics, and those are covered in the standard. The next standard is 1653.1, and this is covering mostly for the traction power rectifier transformers up to 1500 volt. This transformer has the usual service conditions and the design requirement, and this details the loading requirement for the traction application. So we have light, medium, and heavy duty requirement. And the next one is C5732. This is for mainly grounding transformers. As we know, grounding transformers has the special winding zigzag type of connections, and this comes in effect when there is a fault. So this standard requires there are certain things to be specified in the specification. For example, the current flowing in the neutral, and then we have the time the current flows, and the zero sequence impedance in ohms. And the next two standards, C57110 and standard 519, they are dealing with the non-sinusoidal load current requirement and the harmonic enhancement factors. And then we have limits on voltage and current harmonics covered in IEEE standard 519. So all these standards cover the specific points, and the general standard C571200 and 1201 is applicable to these transformers. General service conditions are covered in standard C571200 for liquid immersed transformers and C571200 for dry type transformers. For special application transformers, the same applies, and operating continuously above nameplate voltage under no load condition is 110%, and if it is loaded with a combination of voltage and frequencies shall be limited to 105%. With the temperature limit as specified in general standard for core to meet. And next one is the harmonics. The voltage and current harmonics are specified in standard 519. So it gives what is the harmonics to be limited for the different voltage classes, and that has to be taken care. If the harmonics are more than the limit, then we have to do additional calculations for cooling requirement. And for especially traction application transformers, we have special duty requirement, which we have covered in the upcoming slides. And one of the special thing about the traction transformer is Traction transformers normally goes through many number of short circuits while in operations. So what happens is that we have the current almost 10 to 20 times the rated current flows more often than a regular transformer. So these transformers normally of small type and they comes with the short circuit testing requirement. The standard impedance is normally 6%. If it goes lower than that, there will be special design and manufacturing requirement to meet the short circuit requirement. So the rating data requirement as for these special applications involves something called fundamental kVA rating. So what is fundamental kVA? So fundamental is kVA rating is just RMS value of the fundamental current, and this is used for the commercial loss guarantees. And when it comes to the RMS kVA, which is used for loss and other calculations, it is calculated by RMS value plus the associated harmonic currents. So what happens when the transformer is designed, you will have a base value is increased to provide cooling. The next one is the tapping requirement. These transformers normally have standard tapping requirements on the high voltage side, plus or minus 5%. So there is no complexity in this case. But next is the impedance. So when it comes to impedance, we have a short circuit impedance, which is required by short circuiting all the low voltage windings. And next we have a commutating impedance. The commutating impedance is only it is just one winding which is coming in the circuit, rectifier circuit will be shorted, and the impedance is calculated or tested for that condition. And this is very important for rectifiers when it is changes from one circuit, one diode combinations to next one. So that is very important. Next, we have a winding connections. We have many different winding connections covered in standard. Some of them are circuit 23, 25, and 31. So circuit, say for example, circuit 25 is both HV and LV or delta and delta. And this is like a 6 pulse, it has only 2 windings. When it comes to circuit 31, we have 2 low voltage windings. So this is where we have new complexity, something called coupling factor comes into play. So coupling factor will determine the short circuit reactance and load losses, and voltage regulation also, because certain cases you need loosely coupled or fully coupled requirement. And normally this is specified in the specification. If not, there has to be a discussion with the customer for the design purpose. Next, as we saw the duty cycle requirement in the traction, we will see in the next slide. And the temperature limits for the traction application or in general rectifier transformer is given in table 10 of the standard. For example, if we have a industrial service requirement, then we have special loading arrangement. When the load goes to an increased load, for example, 200%, the winding temperature limit is 140 degrees Celsius. So those requirements are covered in table 10 of this standard. The duty cycle requirement for the traction transformer is covered in this slide. So what happens if the customer specifies just light traction duty? So the standard requires it has to operate continuously 100% load and 150% load for 2 hours, and then occasionally for 200% for a minute. So this is the requirement as per the standard. So when we operate at 150% or 200%, the limit as per the C571810 is 140 degree hot spot temperature for liquid type.
So, Bala, this is a very interesting topic here. Traction transformer, actually, they do have a very specific requirement. And if you see this 2-hour cycle, it is based on the peak load on these transformers. During transit application, these transformers are very heavily loaded more than nameplate rating in the morning 2 hours and evening 2 hours. So that's the reason they're defined, and based on the transit load, they are classified as light duty, heavy duty, or extra heavy duty. And most of the transformers which we see and design and manufacture, they are on extra heavy duty constraints. So actually, it is simulation of a trains going across the various train stations and how the transformer loading is affected. So it's assumed that in these peak hours, it will have continuous load of 150% for 2 hours. And beyond 150%, when there are multiple trains crossing the station, which this transformer is hooked up to, the load will go up to 300% or 450%. So that's how it is classically defined, and they actually equate to the percent run for those 2 hours. So for instance, for extra heavy traction duty, it's 160.3% of the nameplate rating. Now, depending on the customer, they would classify, they may use IEEE for tempesturized requirement, or they may say, we want the regular rating of transformer 65 degrees Celsius rise to be applicable for this RI9 duty cycle, generally known as RI9 duty cycle. So it does need a lot more requirement of calculations, making it thermal stability, the loss requirement, all those things when these transformers are designed and manufactured. And most of these transformers actually go through, because since they're connected to very low voltage rectifier, which is mostly 500, 600 volts, less than 1,000 volts for sure. And they have tendency of having short circuits or heavy load, which is equivalent to short circuit. So that's the reason they have been gone through short circuit testing. And a lot of these transit customers, they want the transformer to be robust. Nobody wants to be getting delayed going to work because transformer failed. So it has a lot of requirement more than the design and all the standard calls for.
So talking a little bit about the design requirements. These transformers normally applied anywhere like design in drive input, drive output, or variable speed applications, generator exciter, traction, and drive isolations. For all these applications, the design concept is different from normal power transformer design. So for example, if you need n pulses in one cycle, so how many number of windings you need is n by 6. Say for example, you want to have 18 pulse requirement. So n will be 3 secondary windings you need. And for 12 pulse requirement, we need 2 secondary windings. And what is the winding displacement you need between the secondary is you can calculate by 360 by n. For example, in this 12 pulse application, you need 30-degree displacement between two secondary windings. For 12 pulse, we saw the most commonly used industrial configuration is ANSI circuit 31, where you have 2 secondary windings, one will be Y and one will be delta. And since we know the difference between the Y and delta line voltage is 30 degree, so that will be used to get this 12 pulse requirement. Another industrial method for the 12 pulse is in extended delta configuration, and we mostly prefer to go for the 12 pulse in the delta and Y configuration, which is ANSI circuit 31. And the coupling configuration plays some importance when it comes to short circuit requirement and loss requirement. And normally that is specified in the specification. So when it comes to winding configuration, when we have 3 winding transformers, which means we have 2 secondary windings, the coupling factor comes into play. So we have 2 different coupling, and closely coupled and loosely coupled. There is one more coupling, partially coupled, which is not used very often, because of strong axial forces. Now, what is closely coupled? So closely coupled is where the impedance between the two secondary windings is much less than the overall impedance. And the construction is shown here, where low voltage winding is in both crisscross configuration. Then we have another configuration that is mainly for loosely coupled.
So these are the configuration which Bala described here for closely and loosely coupled. So one thing to note, these are for circuit 31, where each LB is rated for half of the kVA of the HV winding. So depending on how customer requirement for coupling is, the designer would pick one of these options. So the one which extreme right, you see there do LBs and HV is sandwiched between the two LBs. So LV1 from the core, it will be LV1 on the first coil to the core, second will be HV, and the third will be LV2. So here the DETC taps, which has to come from the winding, has to come in between the duct between HV and one of the LVs. So the other two configuration, which is more common towards the standard configuration of transformers, which are LVs, are closer to the winding, closer to the core, and HVs are outside. It has lesser limitations of bringing HV taps out, but also these transformers, they do have a high current on the LV. So it becomes equally difficult to bring those LV leads out. And the one which is the first one, closely coupled, is probably manufacturing wise is the most difficult one, because you start one of the windings and then you wind second one, and then you take it to the second layer and have a crisscross connection made in between. So all these, they do have different, but this one, depending on the customer requirement or short circuit forces, so it might be needed that job needs to be closely coupled.
Okay, and one more thing is for the loosely coupled, whenever we have voltage regulation linear up to say 450%, then loosely coupled is preferred.
Yeah.
And closely coupled is preferred for having a higher short circuit strength. So this normally comes in the specification or discussion with the customer. Grounding transformers. So the grounding transformers normally are connected in a system where you want to create a ground point for grounding purposes, mainly when you have your system is delta where there is no ground option. And they are mostly, you can have both delta Y transformer as a grounding transformer, or delta zigzag, or just simple zigzag transformer connected to your system for this purpose. In this case, for example, if we just take a zigzag transformer or grounding transformer with zigzag windings, you have totally 6 windings, and the windings, they are connected from one leg to the other leg. So the connection forms in a way that you see the vector diagram here. So we can have this kind of relationship here. And what happens is that when you have a single line to ground fault, say single line to ground fault in phase H3, so the current flows from the neutral, and it flows in the windings A2, B2, and C2. And from B2, it goes to A1. And now A1 is inbound in such a way that the ampere turn in the leg 1 is cancelling each other, because of current in A1 and A2 are flowing opposite to each other. So this phenomenon happens only when there is a fault in the system. What it means is that the zigzag transformer operates when there is a fault. And what is very important here is that customer has to specify what is the continuous neutral current, and what is the fault or thermal current, and how much time it flows in the transformer. So the transformer manufacturer, we do the calculations to meet the temperature rise requirement as per the standard during the fault current. And also, the important thing is that the zero sequence impedance. So what happens when there is a current flows in all three phases, which is a zero sequence current with no phase displacement between them. So this phase zero sequence impedance has to be specified in ohms per phase. And as per standard, it's a must. And if you specify in other percentage or something, it can create confusion in the ratings, because the rating for these transformer can create confusion because of the line-to-line voltages. You see, there are two line-to-line voltages which we can see from here, so that those confusions can arise for these transformers. Coming back again to the rectifier transformers, in these transformers, the design is kind of complex when it comes to the loading and the harmonics requirement. So the harmonics requirement is given in table 11 of the standard C571810, and it gives you for different pulse application what is the harmonic levels for different harmonic numbers. So for example, so for the sixth converter pulse 6, so you will have harmonics 5, 7, 11, and 13, and so on. So with those harmonics, we need to do the calculations for winding eddy harmonic enhancement factor and then stray loss harmonic enhancement factor. So these two are very important for these small transformers and special application design. And this takes into account the percentage of each harmonic current. If harmonic current requirement is not provided in the specification, then this becomes tricky, that we have to use table 11. And as per the standard, the table 11 is kind of a conservative number. So if you don't specify the correct amount of harmonics, either your transformer design can be very expensive, or if your system has more, then the transformer will be inadequate in terms of rating to dissipate the losses. So these are all calculated on top of the I2R requirement. And when it comes to testing, Parminder can talk about this, the additional losses we need to feed during the heat run test.
Yeah, so based on the key factor, harmonic losses are determined by engineering. And so for temperaturized test, those are actually fed, and in addition to the load and no load losses. The total losses which are fed during temperaturized test are more than the total losses of transformer, which generally we calculate. So it combination of no load losses plus the harmonics. So that's how the temperature is simulated in the transformer.
Yeah, so if you notice that Parminder talked about the K factor, and K factor is kind of equivalent to harmonic enhancement factor, but it is different. And K factor is not a recognized term in our standard, the IEEE standard, but it is actually an UL term, which is mostly used in this industry. And K factor is generally means for the use of transformer for non-sinusoidal current as per C57110. So the difference between the K factor and harmonic loss factor is given in the same standard C57110. So what is different is that K factor depends both on the magnitude of the harmonic and the distribution, how it is distributed. So the equation is shown here. And normally it is applicable within the limits of the harmonics requirement from I519. And if it is more, then we have to calculate the additional cooling requirement. Say, for example, if a load is a motor, then the K factor is just 1. It is nothing special. But if you are using a transformer for induction heating applications, normally the K factor will be somewhere around close to 4. If a customer has the harmonic information, then this K factor can be calculated if it is more or less, and the design can be accurate to the specification requirement. And this is very, very tricky, that if K factor is not clearly specified, then your transformer cost can go up quite a bit. And if it is under specified, then it will be a problem in the field, because you cannot cool down for the additional harmonic loading requirement. So that these two are very important for the specification to include.
Yeah, when it comes to testing of these transformers, there are not many special tests required, but the test procedure is different based on the configuration of transformer. Like for instance, if we have a circuit 31 or multiple pulse transformer, which we in the rectifier duty, extended delta, polygon, so those would need some special calculations per se for load losses and and to some extent some for ratio and resistances. And otherwise, the testing wise, it does not specifically say, it doesn't have a whole lot different. But if you look at all these ratio, resistance, ratio probably is some of things. We talk about extended delta. It may not be possible to do ratio tests with the standard ratio meter. So from there, if the angle is plus 7.5%, minus 7.5%, which is very common for multiple pulse transformers, you have to use either an oscilloscope, or there are special meters which would measure the voltage and compare the numbers between secondaries and the primary. Also, it will give a phase angle between the wave shapes. And you would need a three-phase power supply to do this test. So those add some more complexity to the testing, but when you see the results, they would not show you a big difference coming out from table to table. Same way, the no load losses and load losses, the no load losses is exactly the same. You do one supply of one of the winding with the rated voltage. And however, the load losses are different, because now you have multiple sets of load losses. One is for total all secondary windings shorted and supplying the rated current based on total MV of the transformer. That is the total losses and the total short circuit impedance of the transformer. Now, in order for us to get to commutating impedances, we have to measure the impedance of each winding with respect to the primary. So if sector 31 transformer has 2 LV windings, then there are 2 set of ratings. When we have 4 or 6 LV windings, then you have that many ratings from each primary from each second to the primary. Now, in some cases, customer do ask for each secondary to other secondary. It is not very common, but I think that is being used by through some system calculation and the equipment calculation based on their side. When it comes to design test, again, it becomes some more complex as compared to standard transformer. Let's take each one of them separately. Temperaturized test. If we have just simple ONAN and ONAF ratings, then it would be, we have multiple windings, shutdowns to be taken to determine the temperature rises. Whereas when we say overload test, which actually may not be exactly overload, but it is based on the traction duty, and we have to do the extra test for maybe 2 hours based on RI9 cycles, which is commonly done by equivalent rating for, like, for instance, extra heavy duty transformers. It is 160.3%, as I mentioned earlier. But there's some customer, they would like to perform this test on the actual cycle, but just 2 hour 150% and the peaks of 300% and 450%. So we have to, in that case, we have to check our test room capabilities, whether it can supply that high loss for very short time. So depending on the customer requirement, that needs to be reviewed upfront and ensured the testing requirements are met. The one important thing, as I mentioned earlier, it's very important to understand what is the harmonic loss in these transformers and ensure that is fed during the total loss circulation. So impulse and audible sound level. So they're standard, but most of the time the LVs are rated for 500, 600 volts, which are not commonly subjected to impulse test. It's generally designed for 30 BIL, and 30 BIL, if it has a very high capacitance, so the wave shapes is not, it's not, and 30 BIL does not make even sense to do to impulse test. So that is impulse test most commonly is an HV on this side. And short circuit capability test is very common for traction transformer. We have seen every customer is looking for the first transformer to be tested for short circuit of its design. And sometimes they ask us to have it short circuit tested, but sometimes there is a contractor in between or engineering firm who has a contract for the full substation. They would take it. So either way, in fact, if you look at our short circuit test transformer data, most of them are from traction duty. We want to share a few pictures of such transformers. Now, this one is which you see is 36 pulse transformer, and 36 pulse means it will have 6 LV windings. So each winding, each LV is rated for 1/6 of the kVA of the HV winding. So on the left picture, you see multiple crisscross connections which are made. So these are actually making extended delta configuration of 6 windings. So 6 winding will have different parts of extended portion of delta and the delta. So it's very critical to ensure the leads are identified properly, the crimp connections are made, and then the rating which the engineer designs is based on the extended portion is based on the line current of the delta, whereas the delta portion is designed for the phase current. So design itself is challenge, and then having all these connections made. So, and most of these windings are in different portion to keep short circuit forces minimum. So they're not one winding is all clubbed together. They are distributed in the full axial of the transformer. On the HV side, it's not that difficult. Mostly they are in the Y or delta configuration with the DNRS tap changer, 5, 7, or 9 taps, which is very common for such application. And most of these transformers, they do not need any regulation and lower tap changer. At least we have not seen any of multiple pulse transformer to have low tap changer, because they have choice to change the voltages with the rectifiers. So this is a picture from, again, the same transformer, 36 pulse, and you will find the LV ATC is having 18 bushings, and and they are very low voltage because the voltage, as I said, is lower, high current, and you'll see 6 set of bushings with three phases. And most of the time it's difficult for customer, or we work very closely with the customer to ensure the cables which they're going to bring in are going to be aligned up to the bushings. So they are stepped out, sometimes with a bus bar, sometimes just a bushing by itself, and just the cable we supply is required supporting, like the red FRP channel which you see on top and bottom. They are the one to support the cables, so the bushings do not see a whole lot cantilever load on them. So what you will see, this is a small portion of the 18 bushings which in the same ATC.
So the example nameplate for the same transformer we saw, 36 pulse, is shown here. In this case, the 36 pulse transformer needs a phase displacement of 10 degrees between them. And if it is 24, it is 15 degrees, and 18, it is 20, and then 12, it is 30 degree phase displacement between the secondaries. Coming back, in this case, it has 6 secondary windings, and each are displaced by 10 degree between them. For example, LV1 is say minus 25 degree, and LV2 will be 15, and LV3 will be minus 5. So you see the connections at the bottom, it says R1, R2, R3. So it has 18 bushings, and each phase you have 6 of them, and for each secondary windings. And this configuration is in extended delta configuration, where you have the portion outside the delta is for different current, and portion inside the winding delta is different. So the winding construction is kind of complex in terms of lead takeout and everything. And otherwise, for the HV side, it is standard. It comes with the standard DTC or offload requirements. And in this case, it was a 6.7 MVA rectifier transformer with 36 pulse drive duty application.
So our discussion, we went through various special duty transformers and or special application transformers. Our discussion mainly was tending towards oil field transformers. So I would say, all these testing, con construction wise, there's quite a bit similarity between dry and oil field. And however, dries, they do have different temperaturized limits. And so they, based on the material used, based on the process used in dry types, temperature would be determined based on that. Also, another factor which could be different and between circular versus rectangular coils. And as you know, I think you might have heard us earlier, circular coils are always preferred over rectangular. However, rectangular are less expensive and could be done for small rating transformers. So with that note, we are open for questions, and we covered quite a bit details. It's not possible to cover everything, but that's the reason we're giving some time for questions, and also now and it'll be later if you guys need. Thank you. Actually, this is Parminder. I do want to say one thing. Our presentation mainly concentrated on the rectifier duty transformer because the construction, the design philosophy, and manufacturing practices and testing. In fact, the standard itself is different. There are a lot of things which need special attention of those transformers. We didn't talk a whole lot about regulators. But mainly regulators are used for regulating the output voltage from any distribution transformer. Generally, they are 15 kV class, 25 or 35 kV class. We have seen some requirement of 46, not that common, but they're mainly limited to 35 kV class. And the purpose of that is it does not have primary and secondary. It just have a load and source. So the load will source will receive the voltage, and load will regulate with the LTC within plus minus 10%, which is the most common rating. But it could be designed differently as customer want, -5 plus 15, or any other combination. It could be done. One peculiar thing about regulators is that they are rated for some kVA, but a throughput is different than the kVA, because throughput is defined by what power will flow through, and most of the time, depending on the range of this regulation, which is generally 10%, in that case the throughput will be 10 times the rated kVA. So if it is 4 MVA regulator, it'll have 40 MVA throughput power if it has the plus minus 10% voltage regulation. So I'm going to answer some questions, and I have questions.
Do you consider thermal stress due to oscillating loads and the mechanical stress caused by such loads?
Yep. Yeah, so the change in load, how do we consider is we design for higher load, say 161%, So that's how the oscillating thermal load will make sure that the design will make sure that the temperature increases within the specified ANSI limit. So for instance, normally it is 140 degree for 150% 2 hours cycle. So if it changes between 110% and 140%, still it will be within the limit of the design and test results.
Yes, and one thing to add on to that is, yes, the abrupt changes in load, and it would definitely have thermal impact, which is slow, but it will cause some forces within transformer.
Yeah, and then normally the impedances will be in 5-6%. So they are normally designed to take care of the additional short circuit force compared to the regular transformer, means power transformer.
So we don't have any more questions, but we can wait for a couple of minutes. We have a few minutes left in the time, and if somebody has more questions,
As we wait for more questions, also want to just reiterate that these webinars get CEU credits. So please let us know if you need a certificate for CEU credits, and send an email to the marketing email ID that you have in the invite, and we will send you a certificate.
How do you simulate the thermal and mechanical stress of load oscillation during FAT?
So thermal is easy because this oscillation, especially, it will have harmonics loss. So, or you can say the equivalent loss in kilowatt is fed during the heat run. Mechanical stresses are difficult to really test on transformer. They can be calculated, but only mechanical test can be, which could be mechanical. To the winding is a short circuit test. We are not aware of any other test. Well, you have any experience?
No, but traction transformer, they normally ask for short circuit test from a
That's
outside
true.
lab.
Yeah. So traction transformers, and they do have quite a bit stringent testing requirement. So they do one of its design short circuit test. Also, these customers, they do want to set up the transformer and the rectifier as one piece, and then have the complete testing set of tests done. And so that is another thing. So yeah, so that's how test FAT correlates the mechanical and thermal stresses during the field at the time of final testing.
Now, those traction testing, we go to like a third-party lab, like a key.
They are being done in all short circuit testing, and then we actually long time ago we did do one test by bringing some customer asked us to bring rectifier here, but it's not very common practice to do that. So I'm talking about 20 years we did only once.
So usually it's at a third-party lab, like a Kiva lab or something.
Yeah.
Okay.
He said, let's make it clear that I am referring to as load oscillation is, what I'm referring to load oscillation is nature of loading / unloading transformer over and over in short period of time.
Loading is one thing. What he's mentioning is, you increase and decrease the load in short duration. I would think short duration is few minutes or so.
So so basically, if the load changes only for few minutes, only the winding temperature will change, because the winding time constant is only maybe 5 to 10 minutes in that range. But the oil temperature, for it to change, it will take a couple of hours, 2 to 3 hours. So the load change in few minutes will not really increase the overall temperature, because the oil will be still heating up. So generally, the equivalent load testing, 161%, will make sure that the loading can withstand these oscillating loads.
Okay. So the overall rating is considered and tested as an average RMS, not at particular peaks and the normal loads. Yeah.
Can you explain the design of a low sound transformer design, both dry and oil?
So yes, we can talk in general. It was not part of this webinar, but low sound, there are various things which are the various aspects of sound which are taken care during design and of course manufacturing practices. So the, the first and foremost, depending on how low the sound is, and everything is compared with NEMA rating. So NEMA TR1 specifies what is expected sound from with the rating of that transformer in kVA on ONAN, ONAV, and so if it's TR1, NEMA TR1, then no special needs, special things are needed. But if it is lower than NEMA TR1, in that case there are pre design parameters which we do. We have special anti-vibration pads which are supporting the transformer current coil within the transformer. So we're utilizing that at the bottom and on the points where it gets anchored. And that we can achieve couple decibels, maybe 3 decibels with that. But beyond that, when it goes to -5, -6, -10 decibel, we have done actually up to -17, I believe. Then the design has to be reflected going back into the flux density to limit the emission of sound from the core itself. So just remember, this main generation of sound is from the core. So that's limited, either damped via anti-vibration pads, or it is limited by limiting the flux density. So these are few things. I think we do have another webinar which we did sometime in the past.
We did first
On low sound, yes.
On low sound. So
it's available on YouTube.
It's YouTube. So we can share the link with Jenna if you send the link of the low sound, and then that would be helpful. So it gives a whole lot more detail than these couple sentences said.
In fact, all the webinars done to date, the 7 webinars, and this is the 8th one, the video recordings are available on YouTube.
There's one more question. What is the minimum dB? Oh, okay. What is the minimum dBA can be achieved in oil and dry type?
It's very again, we can't say minimum dB. Our reference again is NEMA TR1. So customers thinks, they look into the requirement of where the transformer has to go. Based on that, they'll define what is the decibel requirement they want, and that will be compared to NEMA TR1, and that will be our reference and will equate to that. So as I said, we have done up to -17 decibel below NEMA TR1. When you go very low decibel, so let's say 50 dB, 40, less than 50 dB, the measurement itself become challenging, because wherever you go, your test lab, your test equipment, your factory environment, they have the ambient noise, and that to suppress that noise, either you have to shut everything down, or you got to figure something else. So ambient is a challenge to measure it. Designing probably won't be challenged. Also, every decibel reduction in the sound comes with some price add. So you can have a quieter transformer. Of course, we got to go really low flux density. We'll add many other things to it. So it will just bump up the price. So it's give and take. We can go as low as customer wants us to go, but it will come with the additional material in the transformer, a special precaution, and that'll raise the price.
Okay. No further questions. We will close it here at this point. Thank you all. We greatly appreciate your attendance and your continued engagement. We will be following up post the webinar with you to check on any additional information or anything else we can do to learn more about the information shared here. So thanks again.
Thank you.